All right, I think we'll get started. Welcome to the NCAR Science Briefing. My name is Laura Snyder. I am the Manager of Science Communications here at the National Center for Atmospheric Research. And this is one of a series of trainings that we offer to journalists that, with the idea of trying to give you a little behind the scenes look at the science that's behind the headlines. So today we're here to talk about artificial intelligence and atmospheric science, as you know. And before I turn it over to our expert, I'd just love to set the stage for you and give you a little bit of background. Those of you that are familiar with NCAR may know that we've been around since 1960. And from the very beginning, we've really been on the forefront of Earth system modeling. So, back in the early days, that meant a pretty simple equation that would describe movement in the atmosphere and having a computer solve it. And over the last 60 years, we've had more and more complex equations for computers to solve because they're describing more and more complex interactions. And that means both interactions in the atmosphere, but also the atmosphere with the ocean, the atmosphere with the land surface, the ice sheets, the sun. And so here we are 60 years later, and we have some really sophisticated, complex, fabulous models that help us really understand the Earth system or components of the Earth system and how the Earth system may change going forward. But we are also hitting some limits. Here we are 60 years later. One of those limits is with the amount of computing we have. So for example, even if we could describe every interaction in the Earth system with an equation, and I'm talking, tiny microphysics of cloud formation all the way to large scale changes in ocean currents, it would be challenging to have a computer solve all of those equations at any scale that makes sense. We just don't have the computing power to do it. Some other limits and challenges for us are having enough observations of the Earth system to really understand the current state of the ocean, of the atmosphere, of all those pieces, and filling in the gaps between the observations. And then another example of some limits we're facing is in our forecasts of severe weather and those kinds of things. Our forecasts have consistently gotten better over time, but there's still some things that sort of stump us and confound us that it's challenging for our models to get right, and we're not quite sure why. So we're facing some of these limits and challenges, but it's also a really exciting time because we are experimenting right now with artificial intelligence and machine learning techniques to see which limits can this help us break through, which challenges can it help us address. So it's a really interesting time of experimentation to see what works and what doesn't. And I am just thrilled that we have NCAR machine learning scientist David John Gagne with us. As far as I can tell, every single machine learning project we have going on at NCAR, David John has a role and his fingerprint is on everything. And we have projects across the entire spectrum of all of our fields. So he has a lot of expertise to bring to this. Before I turn it over to him, just a reminder for folks that if you have any questions, please put them in the little Q&A function at the bottom of Zoom. We'll be keeping an eye on that. We'll consolidate those questions, and then we'll ask David John at the end with whatever time we have left. So David John, if you want to take it away. Thank you.
Well, thank you for the great introduction, Laura. I'm going to go ahead and share screen. So good morning, everyone. I want to talk today about kind of give you a primer on machine learning for the Earth system. We're going to, as part of this talk, we're going to highlight first what is machine learning and some of the terminology associated with it, and why are we wanting to use machine learning for the atmospheric sciences. And once we've kind of motivated this, we want to talk about how are we using it throughout the weather forecasting process in particular. But a lot of these steps can also apply to climate science and other aspects of the broader Earth system science community. Finally, we'll end on kind of what are some of the barriers to broader AI usage, and then talk about some ways we're trying to overcome these barriers with efforts at NCAR. So first, I want to start off with what is AI versus machine learning versus deep learning. You see all these terms get thrown around a lot. AI is kind of the most broadest term, and is basically a kind of catch-all for any method for computer systems to perform human tasks. As an example, a kind of more concrete example, AI you consider is the car. It's the thing that is going to take you somewhere. It's the full system. But there are a lot of ways to do AI. A long time ago, people used to do what are called expert systems. So these were very popular in the 80s. You ask an expert how to do a task, and they tell you how they think they do it, and then you try to write a bunch of computing rules. Turns out those didn't work all that well. So instead, we pursued machine learning. Machine learning is a computer system that learns by reviewing large amounts of data. So data fuels our process, and machine learning is kind of the engine that drives all kinds of different applications. It's really good at basically mapping from a set of data telling you to do one thing versus some kind of outcome of that thing. Within the realm of machine learning, there are a lot of different kinds of models of varying levels of complexity. A lot of the attention in machine learning has been driven by what's called deep learning, which is neural networks with multiple specialized layers for encoding space and time information. You can think of deep learning like a sports car engine. It's a much more souped up, powerful, but also more complex and temperamental form of machine learning that can basically take us places faster. It can take us a lot more fuel, but it can also do bigger things in some cases. So what are some of the ingredients for building our machine learning system? Well, the first thing we need is a well-defined problem. We want to, if you want to have good machine learning results, you need to kind of define what you're trying to do and not just be like, I'm going to do machine learning on this thing. So having a good goal in mind, knowing what data are available to do machine learning, you need data. It's a kind of fundamental part of the process. And you also need constraints. You need to know how much time do you have to run your model? What are kind of the physical laws that you need to be following? What are like other regulations, like in terms of government regulations? How are people going to use this? Those are kinds of questions you want to be asking before you even start on the whole machine learning process. Then once you identify these things, you then go and gather your data. Data consists of things like metadata. So this could be the index, the date, the other properties that you're not using to directly train your model, but you need to know to keep track of all the different examples in your data set. We then also have our inputs. So for weather problems, maybe things like temperature, pressure, wind. But basically, whatever data you collect that is abundant and helps you, it has some relationship to what you're trying to do. Then you have some kind of output, in this case, whether or not hail will occur. But it's often some kind of more downstream task or like prediction in the future that you want to have, but you can't currently gather. And finally, you need a set of candidate machine learning models. There are a lot of different ways to do machine learning. You have things like neural networks, and we have methods like decision trees. They both have their advantages and disadvantages. One may work really well on one problem and may work poorly on another, or they may both work well, but one has other properties that make it's faster or lighter. So you want to go with that model. So then this kind of define what machine learning is, but why are we wanting to do this? Why after all these years of building giant Earth system models and weather models and other kind of physics-based simulations, why is everyone really gung-ho for machine learning? And the answer is that machine learning can perform tasks that are called intuitive for humans to do. So like identifying a cat or a dog in an image. But they're also extremely hard to describe formally. People try to do formal descriptions of like what is the shape of a dog's ear in very mathematical ways and hand code that, but it didn't work very well. Turns out that if you just provide enough pictures of cats and dogs or hurricanes and tornadoes, you can give it to the machine learning model and it can say this looks like a tornado and this looks like a hurricane and this looks like a hailstone. Where machine learning also shines is that it can provide an advantage over a human or hand-coded system if it can perform the task either approximately as well, if it can do it faster and more consistently. It's usually easy to do more consistently. Faster is often true with computers, but getting the approximately as well part down is usually the big challenge. and if you could do it better, that's even bigger bonus. But getting to approximately as well is still the big challenge for a lot of new machine learning systems. And the reason why we're kind of interested in this is that we think because we have a lot of tasks that are kind of in this intuitive but hard to program or expensive to run, we think to get over some of these challenges that are present in weather and climate prediction, machine learning might be part of the solution. So to kind of illustrate where some of these challenges lie, we're going to kind of go through the whole weather forecasting process and highlight where some of these challenges are occurring. So the first thing that meteorologists do is they gather lots and lots of observations about what the state of the Earth's atmosphere is at a given time. So we have weather balloons, we have aircraft. There's actually little instruments in the nose of a very commercial aircraft that collects temperature and weather, and we've actually had fewer of these readings over the past year because of the pandemic and people not flying. We also have lots of satellite data. We have buoys and other things in the water. Some of these instruments basically are called in situ. They are like directly measuring the atmosphere, but there's also a lot of remotely sensed data like the satellites and the radars. And they both have their advantages and disadvantages. And we want to be able to process all this data as fast as possible to understand the current state of the weather so we can predict the future. These observations then get fed into our numerical weather prediction models. These are basically simulations that are run on supercomputers that solve all the equations describing the atmosphere forward in time, every hour of every day. We run them forward to see what the next, say, couple weeks of weather are going to look like across the world. These simulations, of course, are approximations, so they have lots of errors. These errors grow in time because of chaos theory. Basically, the initial errors kind of compound upon each other. And so they're imperfect approximations of the future. The models are also expensive to run, so if there's some way we can speed them up, we can then run at higher resolution and get better approximations. We can add more complex physical processes into them and provide more useful information for our weather forecasters. Their job is to take all of the observations and the modeling and turn it into a weather forecast. The key component of going from data to forecast is basically highlighting what are the real threats, where can weather actually impact people, and creating and communicating that information out to the public and other decision makers and so on. Since the forecasters have a limited amount of time in which to look at all this data, are there ways we can help summarize the data and make it easier for them to go from raw weather data to impacts? So now I'm going to highlight a few I call success stories at NCAR where we're using machine learning to assist with these challenges across the observations, modeling, and impact side. So on the observation side, we're going to talk about filling in data gaps beneath the ocean surface. For modeling, we're going to emulate atmospheric chemistry with fewer computing resources. And with impacts, we're going to talk about improving forecasts of hurricane intensification. So first, observations. What's going on beneath the ocean surface? Why do we care about what's going on under the sea? Well, there's a lot of sea creatures that live there, like plankton and fish, and basically, it's the part of the ocean we often care a lot about for all kinds of reasons, and so we want to monitor it and understand the condition of what's going on. To do this, we have a lot of different ways. One is with satellites, because they can see the entire ocean surface, but they can kind of see the color of the ocean and measure the salinity and the temperature, but they can't really see below the ocean surface because there's a bunch of water there. We have probes that we actually release into the ocean called Argo floats. They're dropped off ships, and then they bob around in the ocean for months at a time. They float kind of to the bottom and then float back up and collect measurements along the way, and then broadcast them once they reach the surface out to other satellites that then get archived at around the world. These give us kind of like in situ measurement of the ocean, but while there's thousands of these floats, there's still a lot of ocean that they don't cover. So to kind of bridge the gap between our satellites and our probes, we can try to use machine learning to learn, given a certain satellite view of a piece of the ocean, what are the properties of the ocean below the surface. To do this, we have a pipeline that we take in satellite data. There's different satellites that collect temperature, salinity, and ocean height information. We feed all this information into our machine learning model, which we've tried a number of different neural networks to do this. And these all, to get from the satellite data to our Argo floats, we use a statistical interpolation technique to kind of match up the satellite pixel to the floats to get the best connection as much as possible, and also quantify the uncertainty in this connection. Because we don't know enough to fully say what in this case we're predicting something called the mixed layer depth. We don't know exactly what this is, but we can get a good estimate and an estimate of how close we know. We then do an kind of iterative updating of our machine learning model using lots of observations of this mixed layer depth and lots of satellite imagery. And over time, we get this to converge and provide us with a probabilistic estimate of the mixed layer depth. And you can use this for lots of other variables too. We're kind of focusing on this one as our sort of pilot project. So what does this look like in practice? So if we just use the data from the Argo floats, we just get this view of the ocean where you see these red and white and blue dots. So we know there's stuff going on. We know there's some higher mixed layer depth or shallower mixed layer depth over here, and deeper mixed layer depth over here. And we know what happens on average from these obs, and we can also interpolate in between them. But if we only interpolate in between them, we get a very smooth picture of the ocean. However, we can bring in the satellite image and fill in the data gaps. We can discover a lot more fine scale structure in the data that isn't apparent just from the in situ obs themselves. And this fine scale structure may be important for say monitoring, figuring out where to fish, or if you have a submarine, you might care about where the mixed layer depth is higher or lower because it affects how smooth your ride is. There's a lot of potential impacts. There's also a lot of problems that are kind of like this, where we have basically sparse in situ obs plus lots of remotely sensed data, and we want to fill in the gaps in between. We're using this for things like fire weather, and a bazillion other problems. So that's kind of focusing on the observation side. We're going to move kind of to the modeling portion and focus on a task called emulation. So the reason why we're interested in using machine learning for emulation, or basically kind of creating a surrogate model that runs in place of a more complex model, is that our Earth system models, so the models we use to project what the future climate is going to look like and study our current and past climate, over the past few decades, we've added more and more complex processes into these Earth system models because we want to study things, not just what the atmosphere is going to do, but also how's the ocean going to evolve, how is sea ice and land ice. There's all these aerosols that were released into the atmosphere through human pollution and volcanoes. There's also vegetation and plankton. All these different features of the Earth system can act as carbon sources and sinks. They can affect the weather and climate in different ways. So we need to model them all to get an accurate picture of what's going on. However, each of these models is computationally complex and requires bigger and bigger supercomputers to run. Unfortunately, our supercomputers are also not getting as faster over time as they used to. So back in the 80s and 90s through the early 2000s, you could basically count on whenever you got a new computer, it would have like an exponentially faster processor every year. Eventually, though, because of power, because of how much power and heat that the processor would generate, the computer stopped getting faster, and instead we started adding more cores to the computers. So that's why you have more multi-core processors, but the clock speed, the megahertz or gigahertz on them hasn't really changed all that much in the past decade. This is why. So as a result, our single thread performance, while it's still going up, has been slowing. So we can't just count on our computers getting faster anymore. The computers also require more power because they're just getting bigger and bigger. So if we just want to wait for our computers to get faster to run bigger models, we're less able to do that anymore. So we need some other approaches. We're also running into our legacy of technical debt. All of our models are written in Fortran, which is a really great language for high performance computing and modeling, but the rest of the computing world doesn't really use Fortran very much for their stuff and doesn't interface very well with Fortran. So we're running into the challenge of without we have all this legacy code and it's getting harder and harder to update. What do we do? So the kind of verdict is that our business as usual and our system modeling is becoming kind of infeasible. We need to figure out something different. So one way to be different is to use machine learning in this process. Why is machine learning useful from an earth scientist perspective? Well, earth scientists are really good at designing rigorous modeling experiments, generating tons of model output. We have petabytes of data from things like the coupled model intercomparison project. And scientists are also really good at saying whether or not the results from these model runs are good or bad. They have lots of clever ways to analyze for physical consistency and correctness. The downside of I guess focusing on our system scientists is that they're often a lot of them do have some programming training, but they're not the best programmers in the world. They didn't spend their years of training and learning about their system to also write clean, accessible, optimized, and high performance software. They also are not going to be getting down to the low levels of writing C code to work optimally on a GPU. There are some people in the community that do that, but the vast majority do not. So this is where machine learning can come in. It can take all this data we generate and it can fit a machine learning model to it. The machine learning models basically have a lot of infrastructure written around them to make them easy to train and use because machine learning is being used by the entire rest of the industry and government and everyone else. So lots of people are contributing to machine learning software. And so the earth science community can take advantage of software investments from other fields to increase their productivity via machine learning. So as a result of kind of this potential value proposition, NCAR is supporting multiple machine learning emulation projects currently. There's already quite a few other groups around the world right now to see if we can get a big speed up from our models. So like the ECMWF, the European Center for Medium Range Weather Forecasting, they also just unveiled a machine learning roadmap. So they're like 5 years ago, machine learning wasn't even a major concern to them. Now it's a key part of their future modeling strategy. So coming back to NCAR, one project we're working on for emulation is in atmospheric chemistry. We have a model called GECO-A, or the Generator for Explicit Chemistry and Kinetics of Organics in the Atmosphere. What does this model do? It simulates the reactions that volatile organic compounds undergo. So volatile organic compounds are just kind of chemicals that get released into the atmosphere that are have lots of carbons in them and kind of basically react with other things in the atmosphere and produce lots of other chemicals, including things that are that can be hazardous to people's health. So it can produce different gases and aerosols and increase pollution. Some chemicals, like you can they like emit various smells and stuff, so it can be kind of a nuisance in some ways. But to accurately model all these chemical, like when the reactions that these kinds of chemicals can produce are like hundreds of thousands of reactions and so many chemicals. So we can explicitly run this model forward in time and simulate all these reactions, but it's very expensive to do so. And if we want to kind of say make a model of how these different chemical species are evolving across the United States and use it in kind of a forecasting sense to basically say where is the pollution from these kinds of chemicals going to be really bad. We can't do this with Gecko A directly because it's just too expensive to run. It won't run fast enough to deliver a forecast in time. But if we can emulate Gecko A and kind of like capture the essential parts of how it evolves with a machine learning model, then we can put that model in something like one of our weather models, and then that could potentially then help say a weather forecast, like the Weather Service, they issue more better health warnings for when certain aerosols are really high or expected to be really high, and provide more details about what kinds of aerosols and what their potential impacts are. To do this, we have to generate data. So we run Gecko A for we run 2,000 experiments. We pick kind of sample random conditions for each species across the space of conditions in the atmosphere that we expect to happen. We run the model forward in time, about 5 days in model time. So we get about almost 3 million samples from the model that we can then use to train our machine learning model. What the model outputs are these kind of bins of aerosol and gas concentration over time. It's bin by something called volatility, but the basic idea is that you have this precursor chemical that produces a bunch of gases that eventually evolve into aerosols. And so we want to capture that whole process with the machine learning model. And it's affected by things like temperature and the angle, how high the sun is in the sky, and what other chemicals are floating around in the atmosphere. To really make sure it works, so we first train the model with like we would with a typical neural network, but then we also need to run it forward in time and make sure it works well, because there's a lot of problems where the machine learning model, you train it, and then evaluate it on kind of similar data it's been trained on, it looks great, but then you put it into something that's more like a real life situation and it blows up, it falls flat on its face. So we first give it kind of let it basically run through this time series and use the predictions it's made to feed the next time step in the model. So we run it in a loop, and this is a good test for a machine learning system to see how well it can kind of handle a real world situation. So when we do this, we find that with this problem, maintaining stability in the model is when moving forward in time is challenging. But we tried a bunch of different settings, and we found some that are a lot more stable than others. And then when we did that, we then generated different neural networks with different random initial conditions, optimized them all, and launched them forward. And this gives us an ability to kind of quantify the uncertainty in these predictions. Since it is an approximation, we want to know how uncertain our estimates are. And when we do that, we see we can, the black line from these experiments is a different Gecko run. And you can see the precursor chemical decreases exponentially over time. Then the gas basically spikes in concentration and then decreases again. And then the aerosol at the end of the process will start kind of increase and then sort of flatline over time. And so we train it forward, and we see that we get pretty good performance. We're mostly covering the envelope of the actual simulation, and we capture some of the wavy properties in it. There's still room for improvement. So like in this experiment, we're kind of under predicting the concentration of aerosols, but we're getting the trajectories right. So we're working on further refining this and optimizing it, and generating more data and running this on more species. And now we're going to actually work on putting it into one of the atmospheric models and see how it does when we run it across the whole US. Turning from kind of modeling to impacts, there's a lot of problems where basically weather models generate kind of estimates of like the temperature and rain, wind across the atmosphere, but what we really need is the impact. Like, how is it actually going to like affect people? And machine learning can serve as a way to jump from kind of the physical variables to what measurements we have of how of actual impacts. One form of impact that's particularly bad and was particularly notable this past year was hurricanes. So rapidly intensifying hurricanes, which is defined as increasing the maximum wind speed of a hurricane at least 30 knots in 24 hours, is a particularly bad threat because basically you go from a tropical storm that looks like something you could easily ride out to a Category 5 hurricane in like a day. Then yeah, suddenly you need to evacuate or you need to evacuate a whole big area that could have stayed home and rode the storm out. So basically being able to anticipate these kinds of events is really important from a forecasting and a decision-making perspective. We've gotten a lot better at predicting the track of hurricanes over the past few decades. Intensity, though, and particularly these rapid intensification events, are much harder to predict. We've seen some improvement recently in our predictions, but there's still a lot of ways to go, and it's still a particularly hard problem. For this project, we received funding from NOAA to try out some machine learning and deep learning methods on hurricane predictions to see if we can quantify the uncertainty in our hurricane intensity predictions and identify better when these events are going to occur than some of the existing methods out there for this. So to do this, we have an archive of data from the Hurricane WRF model, basically taking storms that occurred in the 2015 through 2018 hurricane seasons. We run a new configuration of the model for these old storms and to see how the model performs across kind of different situations. We give these storms to the machine learning model, and we do it in two ways. First, we kind of go the hand-derived way, so we calculate a bunch of what we call storm diagnostics. So these are like how fast is the hurricane the predicted hurricane at a given time, what's the shape of it, what are other properties of the storm. Then we also take kind of we do some smaller amounts of processing to basically rotate the storm so they're all kind of oriented in the same direction. And we take the storm diagnostics and feed it to a more traditional dense neural network, and then take the more complex or the less processed data and feed it into a convolutional neural network. So this is a deep learning model, and this is kind of the regular machine learning model. We give them both what actually our best guess of how the intensity changed over time, called the best track intensity change. We train them, and then we have them predict the hurricane intensity change probability distribution. So basically, what's the chance that the hurricane would increase by, the wind speed would increase by 5 knots in 24 hours versus 20 knots versus 30 knots. When we do this, we then evaluate it over the 2020 hurricane season, so what just happened, and see how well it performed. Does this actually add value over the HWRF predictions, and can we actually identify these rapidly intensifying events with more skill than what we could do before? So to evaluate this, we use a diagram called a performance diagram. The idea behind this is you want your dots on it to be in this upper right-hand corner. It summarizes different measures of forecast value. So on the y-axis, we have something called the probability of detection, which says what of all the rapid intensification events that occurred, how many did you capture with your model if you pick a certain like prediction threshold. On the x-axis, we measure of all the rapid intensification forecasts you made, how many are false alarms. So ideally, you want to have no false alarms, and you want to capture all the events. In practice, you usually have to make some trade-off between the two. And what these lines show is like as you increase your threshold for saying rapid intensification, you will inevitably miss more events, but you'll have fewer false alarms. What we found with our research is that in this particular instance, the deep learning model, the red curve, consistently does worse than the shallow machine learning model, which does better than HWRF, which is our kind of baseline model. We have at various points in the curve, we're able to, if you are interested in having more false alarms than misses, then you'll have fewer false alarms if you go with the machine learning model versus the numerical model. The reason why deep learning may not work as well in this particular case is that we don't have a lot of hurricanes to train on. It's a relatively rare kind of event compared with, say, thunderstorms or like just temperature. So we like usually deep learning needs a lot more data and a lot more tuning to perform well. So with an easier to tune model, we're able to get good performance. So we don't always need basically the most fanciest method out there. Sometimes a simpler method is much more effective and easier to manage. What does this kind of product look like in practice? So we have a prediction from Hurricane Laura, which had a rapid intensification event before landfall. The red line is the actual track of how the intensity changed. So the curve, when it's above this part of the curve, we're in the rapid intensification phase. The orange line is HWRF, so it actually kind of predicted rapid intensification in this case. The machine learning models we have, they're kind of called the deterministic forecast from them. So their best guess, they were more conservative than HWRF and said that it would intensify but not rapidly intensify. However, you looked at the probability from the machine learning models, which is the kind of colors in the background, we can see that the machine learning model captured a high probability of rapid intensification. So by using this probabilistic framework, we can identify when there's high uncertainty and also when there's enhanced chance of a rapid intensification event occurring, and thus, if we see this happening, we should probably take precautions to be on the safe side. So with that in mind, what are some barriers to wider AI implementation in weather? Let's do a time check. So I'm going to talk about kind of three broader barriers. The first is unexpected infrastructure costs, then missing last mile connections, and finally ensuring AI systems are trustworthy. One barrier of implementing AI more widely, so like, why don't we see, say, more AI systems running operationally within like, say, the National Weather Service, is that machine learning can save significant computational costs if you're able to use like an emulator or kind of do these other added systems on your observations or your impacts. But to build these systems, it requires a lot of new infrastructure building. You need to generate data for the machine learning models. You need to store it somewhere. The machine learning needs to interface with your legacy model code somehow, and legacy data processing systems. You may need specialized computing hardware like GPUs to take full advantage of something like a deep learning system. You may even need a dedicated server. You need people who know how to run all this and maintain it. You also, since the machine learning model learns just from the data, you may also need to add some other physical constraints and fail-safes to your system, kind of like you would for a nuclear reactor. So you can produce a big reaction, but you need a lot of shielding and cooling towers and all this other stuff to make it work. And the more infrastructure you have to add, the more expensive it is to build. So one of the reasons that like is particularly hard, especially on the government side, is that current weather prediction infrastructure was not built with machine learning in mind, and a lot of it needs to be updated to support machine learning. And we're already seeing issues with, let's say, the NOAA's data infrastructure and serving all the customers that want the data. It's already a big challenge, and there's already outages and other issues along the way to support it. So we need to verify that these AI gains are worth the infrastructure effort to fully recommend that these basically very large agencies and companies should go through the effort to add AI weather prediction and climate prediction into their mix. To kind of help with infrastructure on the research side, NCAR just announced our new supercomputer last week. So HB Enterprise will be building, there's a press release about it if you want to know more information, but it'll be coming online in early 2022. The kind of how this relates to machine learning is that this was the first NCAR supercomputer designed with machine learning needs in mind throughout the procurement process. So we added things like having 20% of the compute on it is coming from 382 NVIDIA top-of-the-line A100 GPUs. We also have further increasing our storage so we can save more data that we can then use to train more machine learning models. We can connect with the cloud to access cloud computing and all the kind of more machine learning friendly resources there. We even used a machine learning benchmark in the evaluation process to see how new computing hardware might perform with on these kind of machine learning workloads. And here's an example of kind of the underlying machine learning problem, which was predicting lightning with satellite data. Going from kind of related to infrastructure barriers are missing last mile connections. So you can build the fanciest AI system in the world and have the nicest model, but if no one's using it, it's effectively useless. To make it useful, we need to be able to interface our AI system into the products that are used by our end users. So as an example here, we have the AWIPS workstation that weather service forecasters use to issue their tornado warnings and other weather forecasts. Currently, it's really hard to add new data streams and visualizations into the system. So forecasters have to basically go look at a website alongside their AWIPS workstation, and adds more friction and time to the process. So this is like an area where we need to spend money on infrastructure to help effectively visualize our AI predictions within our forecasting systems. We also if you want a weather service office to deploy an AI system in their office, you need to train people to run it and maintain it, which is not in their current skill set. We also need to make sure we benchmark standards for operational use. So operational users are very different from a researcher. Researchers have their own things they need to make sure the system runs well and that they're not wasting their time configuring it and maintaining it. So coming up with good benchmarks to make sure that the AI systems we have meet our needs is really important. Along with that, we need to co-develop with the end users to make sure we're building AI systems that solve the right problem and aren't just solving the problems that are where data is easily available. And finally, we need to optimize for improved outcomes. So make sure it's not just minimizing some score, but that the scores are aligned with the outcomes that like we're actually saving lives or getting better, faster communication or whatever the real thing we're trying to do at the end of the day is. There's a good paper that recently came out about this, about some of these issues with deploying AI systems. And one of the things it points out is that if you don't invest time in defining the problem well and collecting data, basically when you get to deploying the model, you have to go and start over again. And starting over again is extremely expensive and wastes a lot of time and can destroy the efforts in some cases. So making sure that you cover the entire AI cycle and not just training fancier models is really important. Finally, we want to make sure our AI systems are trustworthy. So we're a key partner with a new AI institute sponsored by the National Science Foundation and led by the University of Oklahoma, with lots of university, government, and private sector partners, where we're working on building trustworthy AI approaches for actionable environmental science use cases that are also informed by risk communication research with key decision makers in our kind of convergent virtuous cycle. So we're trying to do things like co-develop systems with end users in the process early on. We're also working on developing tools for forecasters that use kind of explainable AI methods to produce new products that can help summarize information for them that would be hard to derive otherwise. In this case, we're trying to take images of storms and identify what type of storm is in that image. So if it's a supercell storm versus a linear storm versus a disorganized storm, each of these has different hazards. Like these tend to produce more tornadoes and big hail, and these produce like high winds like derechos, which have their own properties. And basically, by running this AI system on top of the storm images, we can help forecasters summarize the large amount of model output they have and better identify what hazards are possible and what the uncertainty in those hazards are in their forecasts. So in summary, we're using AI across the whole forecasting pipeline for lots of different applications. We're also dealing with all the various barriers to wider implementation and trying to come up with efforts to address these barriers to help bring AI to the broader weather and climate community and do so in a way that is sustainable and well integrated with everyone's needs. So with that, I'm happy to take questions. Thank you for listening.
Thanks so much, David John. That was really great. We're actually a small enough group today that if people would like to ask questions themselves, feel free to raise your hand and I can unmute you. But I'm going to start with a question we have from Catherine Myers, which is a really great question, which is, does the black box nature of machine learning pose risks when incorporating them more and more into weather forecasting? And DJ, it seems like we have some of the same concerns in NCAR too, with say like a climate modeler who feels really comfortable knowing they understand exactly why the computer is doing the thing it's doing. And if machine learning just makes it better, but they don't really get why, that can make them pretty nervous.
Yes, so that's a great question, Catherine. One of the reasons we have this new AI Institute on Trustworthy AI is because of this black box issue. We in all of our interactions with forecasters and researchers, they want to know why the model is working so they can know when to use the model, when not to use the model, and know if the model is correct. So we're looking at coming up with ways to like validate the performance across a wide range of use cases, and also dig into the models and learn about like what makes the predictions, like why are they making a given prediction in a certain circumstance. So there's ways to generate explanations from the models themselves by basically running the models backwards and seeing like if it predicts a big hurricane intensification event, what fields was it looking at to do so. And there's multiple ways to do that each have their different trade-offs. You can also build inherently interpretable models, so kind of you simplify the model in ways that kind of summarize the key information. You can also build sort of emulators of the machine learning model, so you can build a simple machine learning model that mimics the complex machine learning model, and then kind of interpret the simple machine learning model to let you know about kind of the more complex behavior. It's a very active area of research here and throughout the machine learning community, because a lot of other groups have these similar concerns. There's also the kind of needs for better kind of definitions of what does it mean to perform well enough to be in an Earth system model. Like what are the edge cases that we need to worry about? Where can things go off the rails? And so coming up, like one of the things we're working with a lot of scientists around NCAR to do is further given use cases, where are the metrics that we need to meet that would say this is an improvement, and having them actually go through the exercise to quantify these things. So even if the machine learning model doesn't meet these metrics, now we have a whole suite of metrics we can try for whatever new method comes down the pipeline to try to do this. Sometimes we've even like discovered errors in the current models because we've gone through this exercise and fixed bugs because the models weren't run the way we were wanting them to be run for this machine learning exercise. So there's, even if the machine learning doesn't work out, there's still a lot of other great side products that and good science research and standards that can come out of this exercise.
Yeah, it sounds like it can help you chart a path forward even with a different technique. Like what are the things that are the most important to start looking at in the future?
Exactly.
We have another question from Janessa Duncombe. What are the common misconceptions about machine learning? And I actually, our science team thought about this too, in the fact that we have a lot of science tech reporters on right now. And I wonder if those misconceptions, if you also see any of them in articles you read in the media, like if there are common things people are just getting wrong.
Yeah, I would say some common misconceptions I run into among the scientist crowd is like it's kind of that machine learning is sort of magic that like you just
wait, it's not.
yeah, and it's where people think it's a black box, and it's like it can just find anything, and it's not usually true. Like if there isn't any actual relationship between the data you have and the thing you're trying to target, if you validate it properly, the machine learning model should find no robust relationship between them.
Does that tell you something also when it finds no relationship? Like maybe we thought that those factors in the data did affect this thing, but it really doesn't? I mean,
Yeah, sometimes it sometimes may be a way to test out what factors we thought were important but are actually not. You have to be very careful on that, because sometimes it's like just how the data were formulated or what data you collected. So with any science problem, there's a lot of evaluation we have to do to make sure we're not fooling ourselves, and making sure it's not like, did we just discover a new law of physics, or was it just measurement error? And 90% of the time it's
it's the
measurement
measurement
error.
error, not the new law of physics.
Yeah.
um,
But we do want to try to test that out. I, I think the other misconception is that all machine learning is like big deep learning models that only Google and Facebook can do, and really like those are the ones that get a lot of attention. But what most people in industry and science are using are much simpler models. The basically kind of even at the level of linear regression, but there's still like simple neural networks and random forests and decision trees still power the vast majority of machine learning applications, and do a good job at it. Uh, that said, some of the deep learning methods are because of the investment made in good frameworks to train them. A lot more people are like, as soon as something comes out, like 20 people, a whole bunch of people are already using them in research and even in production. So, um, well, like the yeah, there's probably too much focus on the tail end, and that you must need all the resources in the world to run this. When the reality is, it's actually a lot of the stuff is a lot more accessible that than some companies would want to lead you to believe otherwise.
Thank you. So this is a question from Alex Witzy. Can you talk a little bit about the time frame of discoveries going forward? How quickly do you anticipate the new advances making significant changes in our understanding of basic science?
That's a big question. I would say we're still in the phase on the machine learning, and especially on the earth science side, where there's a lot of people who've kind of started doing machine learning that weren't doing it before, just like adopted in the past like couple years. The funding agencies are finally like on the government side are funding a lot more research. So there's in terms of it's hard to say if like we've discovering the machine learning itself won't necessarily discover the new science, but getting a lot of clever scientists using machine learning in their systems will enable, like I think, us to get to those new science advances. I mean, there like some of the big news stories that things like imaging the first black hole and like the first image of a black hole, like some of the infrastructure behind that was using machine learning to help link all the telescopes together. Uh, on the weather side, where you like there's been some big projects to use machine learning to like identify lots of different storms and climate models, and we're able to kind of open up new analyses to see how things are varying. I don't think I haven't seen like the big huge scientific discovery that's like, well, change everything happen yet, but I suspect as long as the momentum keeps up, some of those will start coming out in the next decade, maybe even 5 years. But there's still a lot of kind of people experimenting, using infrastructure, thinking about it in different ways, and uh, so I think there's still a lot of possibilities. So I would say in the next decade would be the conservative estimate. Probably 5 years would be my less more optimistic estimate.
So we have another question from Janessa. It says, you mentioned the issue of legacy code in Fortran. What are some of the solutions to this issue, and is it being addressed?
So it is being addressed by different groups, and there's I would say two, like probably three different camps. One is you rewrite all the machine learning model code in Fortran and put that, and then you can train it with your fancy Python, TensorFlow, PyTorch kind of framework, and then save it out in a form that can be read into Fortran. So we've done that it works well for like simple machine learning models, but doesn't allow you to give you the full range of flexibility to do the big deep learning models. But it's, in some ways, it's less interconnections and makes it easier to just put some code in, a little bit of new code in the Fortran model and run it forward. You can try to build a bridge between Fortran and the Python world, and some groups are doing that with various methods, but still a lot of making that more user-friendly work that needs to be done. And then the other option, the other extreme end, is to take these climate models and weather models and rewrite them in a more modern language. So whether it be Python or Julia or basically something that interface that's more familiar to the rest of the community. And there are groups that are doing this, and they're like the Klima group is probably one of the more notable ones. That Tapio Schneider is leading at Caltech with other institutions involved. And there's some hybrid approaches out there where they you write Python on top of to connect everything, all the model components together, but still have Fortran under the hood. That's another approach people are trying.
It's hard because we've spent 60 years building these things up, and on the one hand, it's sort of appealing to wipe it from scratch and start over, and on the other hand, that just feels completely overwhelming.
Yeah, it's there's a reason why NCAR is more interested in the methods where we can not have to rewrite our giant community models, but rather add pieces to them. Whereas outside communities or kind of other groups are trying to rewrite the whole climate model. So I think it's good that there's a variety of people doing different approaches, and we can test them all out and see and some will work better for some use cases than others, and we'll see how it shakes out. But there's a lot of interest in it right now because of these computing issues. So and I think it's feasible, and it's already in some ways already being done. So I think it's just a matter of time before the best subset of solutions comes out, and this is a lot easier. It's just, yeah, it's an infrastructure building process that takes time, and not a lot of people have the expertise to do it. So
I want to squeeze in one last question here in our last couple minutes from Stephen Ashley, which asks, will the widespread collection of detailed weather data by the coming Internet of Things, from wireless signals, connected cars, drones, etc., the so-called weather of things, give AI machine learning algorithms a leg up on future weather forecasting? And I guess that's interesting. Like, can machine learning take better advantage of those potentially than our traditional methods too?
Yeah, there's a lot of interest in kind of Internet of Things, or the hot term is edge computing. People want to, like, in some cases, people want to use machine learning to take like crowdsourced observations or the whole network of things and process them and produce a more useful end product, or like convert, say, there's a project at NCAR where they're looking at converting windshield wiper movement to like whether it's raining at a point or not, and then figuring out how to take that information and put it into the weather model. So there's definitely a lot of interest in this. Machine learning has a lot of opportunities, I think, to improve things. The Argo float ocean example is kind of a variation on that, just not with Internet of Things stuff. The problems you run into is the challenges are kind of privacy issues. So if we're collecting a bunch of people's cell phone data, we might inadvertently find out a lot of information about them that shouldn't be revealed. So is there a way if we can collect information without and anonymize it and protect people's privacy, but then still get the weather advantages? There's also, it has Internet of Things weather observations are going to be more useful in areas where we don't have a lot of weather observations. So in like North America, we have tons and tons of weather stations, radars and satellites and everything. But in other parts of the world, especially in the Southern Hemisphere, our weather data is much more limited, but there's a lot of people with cell phones now. So this may be a way to, if we can properly privatize, or say,
Anonymized, sort of.
anonymized. Yeah,
Yeah, if that's a
yeah.
word.
There's a lot of companies wanting to privatize this process, but and are doing so. But there's anonymize the data and provide protections and quality control and ensure that there's also issues with, like, say, people hacking cell phone locations and or spoofing it and, say, issuing fake reports or other things like that we also need to be careful about. And so having good data quality and knowing how we're collecting all these observations will help us take advantage of these systems and give us another leg up in our prediction and impact estimates.
Well, thank you so much, David John. We're at the end of our time, and thank you to everyone who gave us an hour of your busy life. I really appreciate it. Allie, I think, stuck some contact information link in the chat, but I will also follow up with an email to everyone with the video recording of this and also some other contact information. And if you ever have questions about anything atmospheric science related or system related or machine learning related, please feel free to reach out to our media office and we'll help you find someone who can answer your questions. So thank you, everyone, and have a great rest of your day.
Thank you.